For this one, as a tutorial like CADb exercise, I introduced the explanation what is going on about PSS simulation. So suppose that we were simulating in typical circuit analysis. Oh, this is too much zoomed. Then the typical analysis of circuits in analog circuits, we are assuming the operating point is fixed. And then we are applying the small signal. Then we get the output. This was the situation before we simulate, before we do the PSS mode simulation. But now we have to think about how we are changing operating point over time. So for example, we are applying clock here. Then when clock is high, the operating point is different from the clock is low. So it is moving back and forth. This point to this point, and this point to this point. So to model this, there are very, very smart people who mathematically model this kind of behavior as a PSS simulation, which is periodic steady state. So we assume we arrived steady state at operating point when clock signal is high, and we calculate. And when clock signal is low, then we also calculate steady state operating point. And we are moving back and forth, back and forth. And this simulation tries to find stabilized state when the t equal to, the signal at time t is equal to signal at time t plus 1 period later. That means it is stabilized in terms of period, which is in our case clock frequency, a clock period. So PSS converts the circuit at fixed bias point, which is time varying based on clock frequency, into input signal as an input, but the circuit's bias point is time varying. That is modeling method based on the PSS. If you want to read further information, you can check this paper. So you can run the transient simulation first for the functional verification of this track and hold circuit. So let me close all the windows. Okay. So yeah, this kind of very, very simple setup was about CADb exercise 5. And transistor width is 120 nanometer and length is 45 nanometer. So I discussed in CADb exercise 2, if you are not sure what to choose, then I suggest using just 1 micron for the width, 1 micron for the length as a good starting point. But this was true for the amplifier like traditional analog circuit design. When we design switches, then the minimum length and the minimum width are prepared as the starting point. I will discuss about it in the later lectures, probably in the next lecture. So we will move on to the analog to digital converter by the next lecture. Then let's try to give input source a sine wave with frequency, which is 100 kilohertz. So let's see. Just 100 kilohertz and appropriate amplitude 100 millivolt with a DC. We will define it. So the DC, let's say 0.5, and VDD is 1 volt, and the clock frequency, let's just set just 1 megahertz as a simple choice. And as user, we can set transient variable, conservative. And for the transient simulation time, maybe we can just see 3 cycles. No, not clock. So order K. And let's run the simulation. At least 2 cycles of the input signal, right? Then we have input, and we have output, and we have clock. So we can move this clock to the lower side, and we don't need to worry about this initial stabilization. You can see that it clearly shows how it is behaving for the track and hold operation, right? But I think I forgot to add capacitance here. Oh yeah, there is a 10 femtofarad capacitance. So it clearly shows that, right? For the clock equal to high, then it is tracking input. And clock is low, it is keeping the value when it is sampled, and clock is high, it is tracking, and so on and so forth. So this was the question to include in your report V in, V clock, and V out. And the PSS plus PAC simulation. So unlike in transient simulation, ensure only one AC frequency definition exists. So what I'm saying is that when you run PSS simulation, you need to turn this one, to nothing for the input frequency. Otherwise, PSS is confused which frequency should it run for the stabilization, periodic steady state. So you have to select PSS, and now you can just click auto calculate. So now it is automatically set as a clock frequency, which is 1 megahertz. And the output harmonics, you can, as a starting point, you can just set 10. And conservative, automatically decide. And yes, that's it for the PSS. Let's run the PSS simulation. Then it is completed. And there was a note, ensure that no error messages appear in the output log indicating PSS convergence. So what it is doing is actually like, it is calculating PSS here and PSS here and convergence norm and so on. This is the procedure, how it is calculating about this one, PSS. So 1 period later, it is calculating. So we are seeing that from 3 microseconds, it is going to 4 microseconds, which is 1 period later of 1 megahertz clock period. So it is calculating whether it stabilized or not. Of course, this is a very simple circuit. It quickly stabilized without any error. But let's suppose that you are simulating very, very complicated circuit. Then it may not converge when you run PSS simulation. Then in that case, you have to think about how it is stabilized in terms of clock frequency, 1 clock period later or 1 clock period before. And for the PAC simulation, so we can set, right, so PAC, first thing you need to do is make sure PAC magnitude is set to as a 1, which is very important here, PAC magnitude 1, as we do for the AC simulation, AC magnitude. And then let's move on to PAC. So the sweep type, or let's just set 1K to 10 mega, 10 times higher frequency than the sampling frequency, for example. And sweep type, let's set linear, like 1000, because we need a lot of point to see what is going on for the sync function. And the maximum sideband, let's just set 0. So this is above a bit out of scope for this course. So you can set 1 or -1, 2 or -2 to think about how it is shifting in terms of frequency multiplication. So you can take RF circuit analysis course to study more about what is effect of frequency translation or frequency multiplication. So anyway, you can learn the PAC. Okay. Then go to PAC and dB20 and voltage, plot it. Yeah, then you can see that it is as we expected during our lecture slide, right? So it is a linear shape with the sinc function, and it ends around -6 dB, which is as we expected for the 1/2 term. And you can also plot phase here. And the theoretical verification. Verify your simulation results against theoretical predictions. So you can verify this one. So let's move on to Python. I already copy and pasted from our GitHub. So first, let's try to get this data. And CD5 AC. Let's say magnitude, ESB, copy, paste. Oh, we don't need to do this. You can also select both of them and send to table. And you can see it, if the x-axis is aligned, then it shows very nicely all the data points that are both of magnitude and phase responses are organized. So here, paste, you can see that those are tab separated data. So the Python or MATLAB can read it. So let me change this one, just data. Okay, looks good. And here, magnitude and phase. So you can see that it nicely matches, right, for the theory and simulated results. Of course, there are some deviations, but in general, you can see how well it matches to the theory for the simulated and the theory results. Of course, there is some deviation. This is because of finite bandwidth of this switch. So when the switch is on, let's say clock is on, then this one is a VDD for the gate, and the source is, let's say, like it was a 0.1 volt and 0.1 volt, right? Or 0.5 volt, sorry, 5 volt. Then it has finite on resistance. The switch, even if switch is on, there is a finite resistance within the transistor. With this resistance and the capacitance, it forms a kind of parasitic low-pass filter. So that is the reason why we are losing, magnitude response as we go higher frequency. Then it is deviating from the theory, and there is a phase shift. That is the effect. So we will continue to the final part of this CAD exercise 6 in the next lecture. So thank you for attending today. So we will have a short break until 10:05, and we will have the quiz. Thank you.